Here are the solutions to the exercises in Chapter 5. I'll go through each one of them with you. Firstly, this is the first of the 5 little looping exercises that we needed to look at. This is the simplest one. Okay, this is loops1.c. We declare a number. I'm going to declare a long number here just in case the numbers that we eventually start putting into this get out of control, like very, very large. On this particular computer, integers and longs happen to be the same size, but that's not always the case. On a 16-bit machine, an integer will only go up to 32,000 odd, whereas a long will go up to about 2 billion. So if we're going to get up into really big numbers like that, I am going to need longs. So let's move on. Standard for loop. For number equals 1, start at 1, print up all the numbers up to and including 100, increment by 1 every time, print out the number on a line by itself. That's the new line right there, and that's it. Okay, I'm not even going to insult your intelligence by testing to see if that works. I'm sure you can do that. Let's have a look at loops2.c. Loops2.c is not much more complex. This time we need a starting point and the number of numbers. We'll call that count. Start and count. We've introduced 2 new variables and we read them in from the keyboard, and then we start at start and we go up to start plus count. And notice we go up to less than start plus count. We don't go up to less than or equal to. We just go up to less than. Think about why that might be. I'm not going to explain it to you, but remember that we only want, say, 10 numbers. And again, increment the same way, print the number out in the same way. It's a very simple program. Let's move on and have a look at loops3.c. Okay, loops3.c is the first time that it actually starts to get meaty. Let's have a look. We've got our same 3 variables that we had before, but now we've got another one called divisor. That's the number that we're going to end up trying to divide into each of the numbers in turn. Okay, so again it's before. Read in the 2 numbers. Again the same for loop. Exactly the same for loop. Little comment here. Now we find the divisors by trying all the numbers from 1 up to the number. So first we print out the divisors of, say, 10 are. But we don't put a new line on there because we are going to print them out in a great big list separated by spaces afterwards. Okay. So now we need a loop inside a loop, because for each of these numbers we're going to have to test all the numbers up to and including that number to see if it's a divisor. Okay, fair enough. Let's try that. So divisor equals 1, and divisor goes all the way up to the number that we're currently in the middle of manipulating, and including that number. And divisor equals divisor plus 1. So here's the juicy bit. Here's the clever bit. I asked you if you could think of a way to figure out whether a number divides evenly into another. The solution is use the modulo operator. The modulo operator. If something divides evenly, then the modulo will be 0. Remember that the modulo is the remainder after a division takes place. So if the remainder is 0, it must have divided evenly. Okay, so when we divide the number by the divisor and we get 0, then divisor must be, well, it must be a divisor. So we print out that divisor and a little space after it, in case there's another one. So when we've finally gone through this entire for loop, we will have printed out all the divisors. So we terminate the line with a carriage return, and that's all there is to it. Let's see if it works. Okay, compile and run. Please enter a number to start at, and that would be, let's say we'll start at 1 and we'll go up to 12. Okay, so that looks right. Let's look at 6. 1, 2, 3 and 6. Sounds to me like we've got them all. 1, 2, 5 and 10 for 10. Okay, so it's working. Okay, let's move on to the next exercise. This is loops4.c. Now, this is the one where we have to determine whether the thing is prime or not. The only way we can tell whether it's prime or not is by actually counting the divisors. If we end up with two divisors, in other words the number 1 and the number itself, then it must be prime. Sound reasonable? Okay, so let's do that. We've got another variable introduced here. This is going to be a little counter. Every time we find a new divisor, we're going to add one to this counter to tell us how many there are. And then we'll check how many there are at the end. Anyway, let's have a look at that. All of this is the same as before. Aha, there's a little new line. The number of divisors for this particular number is 0 so far. Notice that we initialize this every time through the loop. Every single time through the loop we do this initialization. Okay, moving along. This line is the same as before. Now, we do an extra line here. If we find that the divisor is in fact a divisor, not only do we print out the divisor, but we add one to our count of divisors. Sounds reasonable? Okay, then we get to the end. After we've printed out all the divisors for this particular number, we check to see if there was 2 of them. And if there was 2 of them, then we print out an asterisk. The 2 of them would be, of course, the number 1 and the number itself. That designates a prime. Notice that the number 1 is not prime. It's almost like it should be, but the definition of prime numbers is such that the number 1 is not a prime. Okay, and then we print a new line, perhaps after the asterisk. So the asterisk will be optional. Let's see if it works. Compile. Run. Number to start at, 1. How about finish with 12? So notice there are asterisks next to 2 and 3 and 5 and 7 and 11, and that's all. If I'm not much mistaken, those are prime numbers, each one of them. Okay, now let's get into this efficiency nonsense. Try and run the program again. Please enter a number to start at. How about we start at 1 billion? That's what's that? That's 6 numbers, so that's a million. 3 more zeros is a billion, and we want to print out 10 of them. Alright, let's see. Pay careful attention here to how long it's taking for each number to come up, and go. Okay, well they're coming up. We're just doing the first one at the moment, a billion. And how fast is it coming up? Well, it's taking its time. Whew, we could be sitting here for a long time if we want to actually see 10 of these. So what I'm going to do is I'm going to kill this. I'm going to use Control-C to interrupt it and move on to the next exercise, because you can see that that is actually happening quite slowly. So anyway, let's do that now. Okay, this is the final one, loops 5.c. Before I go and have a look at the code, let's see whether it runs and if it runs any faster. Okay, run the project. Okay, number to start at was a billion. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Please enter the number of numbers, 10 again. Let's see if it goes any faster than it went before. Whew, it's done, it's finished already. Everything, all of them, all 10 of them. And how about that? 1,000,000,009 is a prime number. Okay, excellent. Now let's see the magic trick. How did I make it faster? Okay, scroll down, scroll down. This is a new line, and this is new as well. And now we've got a clever bit down here. Okay, so I think we need to have a look and properly understand what's going on here. First of all, we set max, whatever that is. Well, let's just check what it is. Well, it's just yet another long. Okay, max gets set to the number that we're playing with, like a billion. And the divisor does not count up to number, it only counts up to max. Well, at the beginning of the loop, number's equal to max, so it is going to be counting up to number. But I'm getting the idea that max may actually change. We may not actually have to count up as high as number. We may only actually have to count up as high as max. Let's have a look. So, if this number divides evenly into the number, print out the number. Now, while we're printing out the number, we can also print out the other half. So I'll give you an example. If if we were testing to see whether 2 goes evenly into 12 and we found that it did, we could not just print out 2, we could also print out 6, because 2 times 12 is 6. So why not print out both those numbers? So I can print out one down here and one up here, but I want to make sure that they're not the same. I don't want to, let's say if I was testing to see whether 3 goes into 9, I'd find that it did. So I'd print out 3, and then I don't want to print out 3 again, because 3 times 3 is 9. So I just want to make sure that the divisor is not the same as number divided by divisor. Think about that in respect to the 3 times 3 equals 9, and you might see what I'm talking about. And add 1 to the number of divisors. Now I know, yes, there are actually 2 divisors. There's the number itself, like 2, and then there's 6. 2 times 6 equals 12. But I'm really just going to count the pairs of divisors this time. I'm not going to count all the divisors. Now the clever bit. Here's the code that makes the program so efficient. We're actually going to change what max is set to. Remember that max is how high we go in this loop. We don't have to loop all the way up to 12, because if 2 goes into 12, and it does, and it gives you a result of 6, then theoretically, if you think about it, you never have to go higher than 6, do you? I mean, there's no point trying to see whether 7 goes into 12 evenly, because it won't. There's no point trying to see whether 11 goes into 12 evenly, because we know that doesn't either. So that's what this is about. Anytime you try a number, then reduce max by number divided by that number. So let's think about it like this. So when let's say that number is 12. We're counting all the divisors that fit into 12. The first time through it'll be 1, and that's not really going to do much. The second time through it'll be 2. So divisor will be 2. So 12 divided by 2 is 6. So now the maximum number we have to count up to is 6. Next time through, we'll be playing with a divisor of 3. 12 divided by 3 is 4, which means now we only have to count up as high as 4, which is the very next time through the loop. Isn't that interesting? What you'll find out is that if you do the mathematics, you'll find out that you only ever have to count up as high as the square root of the number, or approximately the square root of the number. The square root of 12 is not an even number, but never mind. You never have to count up higher than 4 when it comes to 12. So with a billion, you'll never actually have to count up higher than the square root of a billion, which is, anyone? I think it's... no, I don't know. Let me just take a pause and I'll find out for you. Back again. The magic of television. It's about 31,600. So we don't have to count up to a billion, we only have to count up to 31,000. Now that is much, much faster, as you can probably imagine. Okay, so that's about it. Before this said if the divisors equals 2. Now we're actually counting the pairs of divisors. So we see if the pairs of divisors, if there's one pair, then it's a prime. So we print out the asterisk. And that's it. Okay, we'll just have a quick look at the project, and then we'll be done for this chapter. Okay, here's our database.c again. This one's slightly modified from our original. This one will be in the Chapter 5 course project folder. And again, it's all the same stuff. We just made one slight modification. We've got this forever loop, and we've got this break down here. So this time it will now continue looping around until they've either entered an A or an S. And we saw that before, so I don't need to go into it now. Let's move on to the next chapter.